All right, great. So it turns out that title was a mouthful, so I've shortened it for after lunch on Thursday. I'm going to tell you about H1 disk statistics into the SKA and ngVLA era, and the essence of what I'm going to talk about today is shown on this slide. So the idea here is that what we want to do is get basic structural properties of the H1 disks of lots and lots of galaxies. So what I'm showing you here would be a rotation curve, but we might be interested in surface densities as well. I'm just going to focus on rotation curves mostly today. And what we want to do is get large statistical samples to confront predictions from cosmological galaxy formation theories. And that's what's represented by the cosmic web in the background of this slide. So what I'll tell you about today, I'll describe a little bit about measuring the statistics of H1 galaxy structure. I'm going to tell you about untargeted H1 surveys that will happen through 2030. There's a lot happening in this field in the next couple of years, and then I'll move into the SKA and ngVLA era. So we've heard a little bit about H1 in disk galaxies already, but mostly from the perspective of the baryon cycle. And what I want to do is use H1 as a tracer of galaxy structure. And the reason for doing that is illustrated on these two pictures. So these are H1, these are composite H1, the stars and star formation images from the THINGS survey. So the galaxy on the left is a star-forming dwarf galaxy, and the galaxy on the right is a Milky Way-like system. And in both panels, the blue represents the H1, and the pinky purple represents the stars and the star-forming gas. And so if we start on the right-hand side first, the H1 distribution in a Milky Way-like galaxy extends well beyond the stars. And so if you're trying to understand how the baryons connect with the dark matter halo, then H1 is a really good tracer to use. And then if we go to the left-hand side, there's a lot more cyan in this picture than there is pink or purple. And that's because the cool and cold baryon budget in low-mass star-forming galaxies is often in the H1. So if H1 presents a really efficient way to follow up these galaxies or to look at these galaxies and to try to understand their structure. So there's a lot of good reasons to try to measure the H1 content, morphology, and kinematics of galaxies in order to probe their evolution. So I'd like to tell you a whole bunch about the science, but I'm going to get yanked off the stage if I do that. So I'm just going to give you a bit of a feel. So lots of reasons why we might want to understand the statistics of H1 disks in the local universe. So far what we have are literature compilations of lots of different projects that have observed for lots of different primary science reasons over many years. And so one of those compilations is called SPARC. It's a collection of H1 rotation curves and surface density distributions. There are somewhere between 300 and 400 rotation curves in this sample. And what you're looking at here are rotation curves that are color-coded by the stellar surface density. So there's clearly a correlation here. And what we really like to do is understand rotation curve shapes as well as the variety of those shapes at a given stellar mass. And we've played the game of comparing rotation curve shapes to cosmological predictions for a long time, and there are still tensions when you make those predictions. One of them, and one of the more recent ones that has been revealed, is called the rotation curve diversity problem. In other words, at a given stellar mass, we see a wider range of H1 rotation curves than are predicted by cosmological simulations. And this is a really busy plot that's shown here on the right, but basically the y-axis is an inner measure of rotation curve amplitude, and the x-axis is an outer measure of rotation curve amplitude. And the green and the red points represent simulations, and the blue and the black points represent observations. And the point here is that there are blue and black points at places in this diagram where there aren't red and green points. That's the tension. And so what we'd like to do is be able to understand how that tension arises. And in order to do that, you really want to look at a population level, and that turns out to be really difficult to do because when you're using historical literature compilations of rotation curves, it's impossible to write down a selection function, which means it's impossible to know whether you're comparing apples to the simulations. And so the state of the art in terms of H1 disk statistics is population-wide studies using well-defined selection functions, and that's where we're sort of going into the future. So the other thing we'd like to understand is H1 as a function of cosmic time, and this picture has been shown already. I put it together a couple of years ago. I'm glad it's really useful. And so you can ask the question of what we know about individual H1 detections at redshifts larger than 0, and the answer is not much. Okay. So the vast majority of individual H1 detections that we've made so far are at redshifts less than 0.1. We know of a few dozen H1 detections between 0.1 and 0.25, and until very recently, the record holder was a redshift of around 0.4. We now know of a gravitationally lensed individual H1 detection at 1.3. But the state of the art is that we really don't know very much about H1 in galaxies beyond the local universe. All of this is set to change in the next 5 years or so. And so what I'd like to do is run you through the suite of untargeted H1 emission line surveys that are taking place at facilities around the world in the next 5 years or so. And the overarching message is that there are tens of thousands of hours and hundreds of researchers that are being devoted to these problems in the next 5 years. So it's a really exciting time. And I'm going to use this map that has a couple of optical survey markers. So the yellow dots are the Sloan Digital Sky Survey, if that helps you orient yourself in the sky. But in the next couple of years, we'll get full sky coverage from a set of new surveys. The WALLABY survey on ASKAP in the south that'll have relatively high angular resolution, and crafts on FAST, and the CHORD telescope will do an H1 survey in the northern hemisphere. It will go deeper, or they will go deeper at correspondingly lower angular resolution. There are also medium deep surveys. So MALS on Meerkat is actually an absorption line survey, but it will make for a decent untargeted H1 emission survey as well. Then there's Aperitif on Westerbork. Together they'll cover around 1,000 square degrees out to a redshift of 0.2 or so, and deeper statistically in terms of H1 sensitivity. And then there are the deep surveys. There's Mighty H1 and Fornax, both on Meerkat. Those will cover 60 square degrees. And then the true pencil beam surveys, Laduma on Meerkat, Dingo on ASKAP, and Chiles, which is already complete on the VLA. Together they'll map about 30 square degrees. That's actually driven by the ASKAP field of view, and they'll probe galaxies out to a redshift of 1, and that's driven by the Laduma sensitivity. So there's a ton of H1 observations and H1 surveys that are going to really change our view of the H1 sky that are going to take place in the next couple of years. So one of the ways to look at this evolution is in terms of detection statistics, and that's what's being illustrated here. This is a slide that Brian Gainsler put together that sort of shows number statistics and sky views going from the high-pass survey in the 90s through to Alfalfa, through to WALLABY ongoing now, and then the statistics expected for the surveys in the next couple of years, such as CHORD and the DSA 2000. We haven't heard a lot about the DSA 2000 in this conference, but it's worth noting that if it is built and it runs the surveys that are being talked about now, it's going to run it will be a fabulous northern hemisphere H1 survey instrument. When you're talking about spatially resolving galaxies, though, the metric to keep in mind is column density sensitivity. And in that context, this is a really useful diagram, first put together by Erwin de Block. So the y-axis shows column density sensitivity, and the x-axis shows angular resolution. Each point on this diagram shows an H1 map, generally from a sort of historical observation. And then just to orient you, the typical edge of an H1 disk is at about 10 to the 20 atoms per centimeter squared. So in order to be able to map H1 in galaxies, you want to be below the 20 on the y-axis. And if you go to the left on the diagram, you're at high angular resolution, and as you go to the right, you're at low angular resolution. And you can clearly see that a lot of those points lie in a diagonal line, and that's because you can taper interferometric observations to pay in angular resolution to gain column density sensitivity. And so there's a number of different surveys and objects on this plot, and you can pick out your favorite one. But what I wanted to point you to were the two diagonal green lines, which represent the SKA and ngVLA after about 10 hours, or the SKA or ngVLA after about 100 hours. And of course, better down is better, is more sensitive in this plot. And so both the SKA and ngVLA are going to be extremely sensitive telescopes. They're going to allow us to image H1 disks at resolutions as high as an arcsecond and with column densities as good as 10 to the 17 in about the same amount of time that it would take to build an H1 map for, say, a Things galaxy. You're going to go tens of times better in resolution or hundreds of times better in column density sensitivity. So they will be fabulous instruments for H1 imaging. So I want to talk a little bit about the practice or the mechanics of resolving H1 disks in wide field untargeted surveys. And the survey that will have the best statistics in that respect is WALLABY on ASKAP. So the WALLABY survey will image most of the southern sky, and at 30 arcsecond resolution, which is sufficient to spatially resolve large numbers of galaxy disks. And that's what the histogram on the left-hand side shows. So it's the number of galaxies as a function of the number of resolution elements across the x-axis. And for all intents and purposes, you can look at the purple histogram. And if we consider a galaxy spatially resolved as one that has 4 beams across the major axis, and that's the threshold above which we think we can kinematically model these systems, then WALLABY is going to spatially resolve around 8,000 H1 disks. So that's better than more than an order of magnitude more than we have now. And on top of that, we're going to be able to specify a selection function. So we're going to be able to do statistical studies of H1 disks in the local universe for the first time. Now on the right-hand side are velocity fields from the WALLABY pilot survey data. So ASKAP is producing beautiful H1 data, and WALLABY has entered the full survey phase. So it's a really exciting time for the survey. So what we'd like to do is take all of these detections, or what we would like to do for scientific reasons is to model these detections in order to extract things like a rotation curve and a column density distribution. So if you've ever heard of kinematic modeling or tilted ring models, these have a very long history upon which we're building. We're in a resolution regime where those models have to be run directly on the data cubes instead of on the velocity fields like what I'm showing on the right-hand side. So we're in the regime where we're making 3D kinematic models in order to extract structural properties. And it's important to appreciate that when one works with untargeted survey data, almost by construction, one is working at the edge of resolvability and the edge of detectability. And that's not just true for WALLABY, it's true for any untargeted survey that will be run in the future. So the statistics from an untargeted survey, as well as a lot of the interesting sources, are found at the edge. And so it's forcing us to focus on automated 3D models with statistical uncertainties in terms of tilted ring modeling. And that's a regime in which we haven't really thought about anymore. And there was a video that was supposed to be flipping by, but don't worry, you couldn't have seen it anyways. The average signal to noise per WALLABY detection pixel is less than 2. It's somewhere between 1 and 2. They're very difficult to pick out by eye on average. The moment maps from the source I was showing you are shown here on the left-hand side, and we just managed to kinematically model it a couple of weeks ago, so it's really hard going. A lot of this work is happening within the WALLABY technical working group on the kinematics pipeline that I lead, and there's also been some work, or a lot of work done within the Serata project that's already been mentioned today, and there are 2 really nice papers that describe the first data release for WALLABY as well as the kinematic models. There's also posters by Nathan Degg, who's here, as well as by Alex Gasser, who's working on modeling warped galaxies. So where are we right now? We've done the first public release of over 100 automatically modeled untargeted detections. So this is the largest such sample that has ever been produced. We're sitting on another 150 detections, getting them ready for public release as well, and that should happen a little bit later on in the year. The plots on the right-hand side give you a sense of the data quality. So the top row is rotation curves, and the bottom row is surface density distributions, and we're working really hard on those error bars in order to provide statistical samples to do statistical comparisons, because that's the key science here. There's been a little bit of talk about RFI at this conference. It scares me a lot more than we've been talking about, though. And this is one of the reasons why. This is a really nice paper by Ofringa a little bit earlier this year. It's a waterfall plot, so frequency is on the y-axis as a function of time on the x-axis. And this is between 1100 and 1300 megahertz. And what it illustrates is the waterfall plot before flagging on the left and after flagging on the right, and all of the white are the areas in which the data have been flagged out. So essentially, H1 surveys are currently avoiding 1.1 to 1.3 gigahertz, which works out to a cosmic history of redshift of 0.9 to a redshift of 0.22, which means that effectively, so this is and I should say this is not unique to this particular study. All of the telescopes of which I'm aware around the world are avoiding this redshift range because of RFI. And so what you're increasingly seeing are hatched regions in diagrams. So the colored regions are predicted detections, whereas the gray hatched region are regions that will likely be lost to RFI. So for all intents and purposes, we are losing redshift ranges already and possibly irreparably. So if we go back to this picture about stepping out in cosmic time, I mentioned that the current state of the art is that we know very little about H1 in individual galaxies today. I talked about the prospects through 2030, where we're going to start to map galaxies in the local universe, and we're going to detect them out to redshifts as high as 1. So that's through 2030. What will we do with the SKA from 2030 to 2035? Well, one of the things that it could do is a large survey. So let's swing for the fences. Let's imagine we spend 10,000 hours with the SKA. What could you do? You could detect H1 out to a redshift of 2, and you could map H1 in galaxies like the Milky Way out to a redshift of 1. So we can compare where we are today to where we could be in 2035, and it's pretty exciting. Where will we be in 2035 with the ngVLA? There's a lot of H1 science that's going to happen between now and the onset of the ngVLA, but with an ngVLA at full sensitivity and an SKA well into its operations phases, I think we could do some really interesting things. So what the ngVLA, I think the key synergy here is its capacity to map CO at all redshifts. So we've already seen both of these plots. CO as a function of the observing frequency as a function of redshift is shown on the left-hand side, and then a model of a disk at a redshift of 1.7 imaged with the ngVLA and then with ALMA is shown at the top. And so just off the top of my head, things that you could do, you could take samples of H1 galaxies observed with the SKA and observe them at much higher resolution and in a different tracer with CO. We play this game in the local universe already, and it's really, really fruitful for understanding galaxies. So that's what's illustrated here in the middle. One could imagine imaging CO disks at redshifts at which we cannot image H1. So for example, a redshift of 0.1 to 0.2, it may be that the only way to map disks in a statistical way is to go to a different tracer. And then there's always the possibility of constructing detailed maps in H1 and CO, either with the ngVLA on its own or with a combination of the SKA and ngVLA, not only in the local universe, but as a function of cosmic time, and much, much more. There is so much science to be done between now and 2035 with so many fabulous instruments at so many different frequencies that who knows what we'll be doing at this time. But the point of building large, flexible, generational facilities like the ngVLA and like the SKA is precisely to do great science, whatever it might be, whenever both are available. And so I'm really excited for that. I won't walk you through that because I'm about to get yanked. Thank you.
Okay, questions for Kristine? Yes, back there, I saw Douglas.
Thanks for that. I was interested in what you said about direct 3D data cube modeling, because I've always found rotation curve things unsatisfactory because you compress everything down to this 1D thing, and the best fit isn't a good fit anyway, and you don't know how to do the error bars. And so is there genuine progress on direct modeling to fit the data in the 3D data cube? Is there something?
Yeah, so when you have an angular resolution that's less than about 8 beams across the major axis, you lose information in taking that moment for technical reasons that we don't need to go into. And so there's now a number of different ways to sort of, so the basic idea is the same. You're fitting a set of nested tilted rings, but you're doing it in 3 dimensions, which means you're applying the effect of that you're smearing in the right dimension, which means that you're able to preserve a lot of that information much better. So we can reliably go down to about 4 beams across the major axis, which in terms of an untargeted survey means that we're, that's 80% of the detections are between 4 and 8 beams or something like that. And so we're making real progress. I'm happy to tell you more about it.
Okay, yeah, I should read the papers clearly. It's good. Thanks.
Any online questions? Oh, Jennifer? Oh, okay. Next, yeah, Tom.
Thank you. The RFI issue that you were talking about, do you know what the source of that RFI is between 1.1 and 1.3 gigahertz?
So it's satellite-based RFI, but I know there's more experts in the room. I'll let Tom chime in. I know you've worried much more about this than me.
It's mostly navigation and satellites, GPS, things like that, and airplanes as well.
And what?
Airplanes.
Airplanes, okay. Is there any way that those usages could be moved to other frequencies in a frequency sharing regime? Or are they really fundamentally stuck at those frequencies for technical reasons?
So I mean, I think we've heard how that kind of policy change is extremely slow, and a lot of the surveys that I've talked about today aren't keeping visibilities, right? And so I think there's a possibility in the long term, and then there's possibilities for technological innovation. We've heard about that as well. But this is already a massive problem. We are losing windows of cosmic time.
Okay, great. Well, let's thank Kristine again.